Today's the last day of class, lecture 35, and we're not really doing an ordinary lecture. To help prep you for the final exam, we're going to go over old exam problems to help you get ready. Your exam will contain problems that are pretty similar to a random sample of these problems from old exams with changed numbers, changed functions, changed wording. And I do reserve the right to perhaps make the problem a little bit more challenging if it was maybe something that you should have been able to do more easily than before. So you need to not just put stuff on your note cards, but also understand. Okay, we'll talk about, actually at the end of class, we'll talk about what you can bring to the final exam as well. This will be beneficial for future students too. Not that you'll have the same types of problems, but just learning how to problem solve, learning how to think. And along the way, we'll try to not just solve problems, and I won't have time to solve them all, by the way. I will mostly just give guidance. But you should, especially if you're going to be taking Calculus 2, you should be thinking about, especially the Exam 3 content. And if you did not do well on Exam 3, that should be a big signal that, hey, you need to study this stuff before you take Calc 2. Okay? Think of that as something you should study at least a week before Calc 2. And you can watch my old videos too, if that helps. And maybe this video. So let's go through Exam 3 to start with, and then we'll work our way backwards through the exams. And at the very end of class, I'll try to put everything together and tie off that bow that I talked about conceptually. I guess I am essentially going to give you the answers for the true-false, but again, on the final exam, I might change the wording. So true could become false and vice versa, or maybe not. Maybe I won't change the wording. So it's something to watch out for. So the first one is f prime is positive over an entire open interval, then f is increasing. That is true. That is essentially the increasing function theorem that says when the derivative is positive over an interval, it will be increasing. There are extra hypotheses in there, like differentiability and continuity. But those hypotheses are already contained in this fact right here. The fact that I'm saying the derivative exists and is positive means the function will be differentiable and continuous. Okay? So those hypotheses are already in the question implicitly. So that's why this is a true question. Number two, the function x cubed is indeed increasing over the entire line. That is true, but this is not true. In fact, f prime of 0 is 0, not bigger than 0. 0 is not bigger than 0. Okay? It's greater than or equal to 0, but it's not strictly greater than 0. It's not true if a function is increasing that the derivative will always be positive, even if you assume the derivative exists everywhere. Number three is also false. How does it start off? X to the fourth has a critical point at 0, and you can confirm that. That is true. F double prime of x in this case, or f prime of x is 4x cubed, which is 0 when x is 0. So 0 is a critical point. However, there's a local min at 0, even though f double prime of 0 is 0. Oops. Okay. Yeah, f double prime of 0 is 0. But that doesn't mean there's not a local max or min. That's what I'm trying to say. If you graph the function, it does have a min. So you need to think about graphs as well. This is the example that's just very flat near 0. So even though f double prime is 0, which means the second derivative test doesn't tell you anything, there is in fact a lower min. In fact, it's even a global min. That's the lowest point. It can never be below 0. And that makes this problem false. 4, the inverse sine function does not satisfy the mean hypotheses of the mean value theorem, and therefore does not satisfy the conclusion. That's false in two ways, in fact. It actually does satisfy the hypotheses, and therefore it also does satisfy the conclusion. But also, just because something doesn't satisfy the hypotheses doesn't mean it fails the conclusion. I'll say that again if that was confusing. So the inverse sine function has a graph that looks like this. From -1 to 1, that's the domain. The range or image is from -π/2 to +π/2. This is continuous over the entire closed interval from -1 to 1. It's also differentiable on the open interval. It's not differentiable at the endpoints. You've got vertical tangents there. So it fails to be differentiable at the endpoints. But it is differentiable on the open interval when you do not include the endpoints. Therefore, it does satisfy the hypotheses of the mean value theorem, and therefore it will also satisfy the conclusion. There will be at least one C where the slope of the tangent equals the slope of this secant line. In fact, there are two places, right about here and right about here. But again, I'll say for emphasis that just because a function doesn't satisfy hypotheses of the theorem, that does not guarantee it's going to fail the conclusion. It could still satisfy the conclusion. That's the other big picture item. So in a sense, this is false in two ways. Number 5. Quickly compute the derivative that you see there, the derivative of an integral, where the variable for this function, you can see is t because I'm differentiating with respect to t. Zoom in if you need to, if that's kind of small. It's in the upper limit of the integral. I've said numerous times when we started talking about integrals that that means the derivative of this function must be the integrand, the function you're integrating. In other words, this function right there is going to be the answer, except you also have to plug in t, the true variable. So the answer is e to the sine of t. Common mistakes were to put e to the sine of u, or e to the sine of t dt, or e to the sine of u du. Don't put any dt or du there. The answer is this function that you're integrating. That's this second fundamental theorem of calculus in chapter 6, which I really emphasized a lot. How have I really emphasized this? Besides the symbolism, I've also emphasized it in terms of signed areas. Or let's just think areas. Let's imagine the graph of the function is above the axis. If I let the right endpoint of the interval here be a variable, imagine letting that change, letting it increase. So the area gets bigger and bigger. The derivative of that area function as a function of t, this quantity right there, is a function whose derivative is f. This function right there. Derivative of this area function is little f. It's the function in the graph. It's important to understand the distinction between these things. This curve is the function that I graphed. It's this thing. It doesn't matter what I call the variable for that. Okay, it's the function whose outputs equal to e to the sine of whatever the input is. It doesn't matter what you call the input. The area function is the integral. This thing, a of t, that gives you this area, is the integral from a of t of the function that I'm integrating. The definite integral represents that area. And again, if the graph goes below the axis, it represents a signed area. In this picture, for this particular t that I picked right there, a of t would be negative, because this area is bigger than this area. That area minus this area would be negative. This fact still holds. The derivative of the signed area function still is the original function that I graphed. Okay? If you're going to be in Calc 2, this is one of the most important things to get. You've got to understand this. And we've done a lot of examples with distance and speed, and with, for example, flow rates, which comes up later in the exam. Number 7. is to use a linearity property of integrals. We're trying to find the integral of the linear combination 3 times f of x minus 9 times g of x. Based on knowing the integral for f and the integral for g. The best way to show your work here is to write this. 3 times the integral from -2 to 3 of the function f of x minus 9 times the integral from -2 to 3 of the function g of x. Now most people did not show that step. Okay? I still gave plenty of people full credit for this problem because they showed the next step after this. But realize this is really the best first step to show. And maybe if I put this on the final exam, I might say show this step first, because it was clear some people didn't understand it. This is a special case of this fact. We got 2 functions f and g and 2 constants c and d. The integral of this linear combination will be the corresponding linear combination of the integrals. Okay, and you should be able to show this step, and I might on the final exam, if I put this kind of problem on the final exam, I might ask you to show this step. In this example, C is 3, D is -9. -9 there, which is equivalent to subtracting 9 times this. It doesn't matter what the limits of integration are as long as they stay consistent. That doesn't matter. Anyway, to finish off this problem, now come back to the screen here. The integral of f is 11, and the integral of g is -4. So you would write 3 times 11 minus 9 times -4. Many people wrote that, and I gave you full credit for writing that. Also, if you simplify correctly, did I do the right thing? This seems like it's different than what I thought it was. This is your exam 3, yeah, okay. So you're going to get 33 plus 36, 69. I was thinking the answer was different. Make a mistake somewhere. Does everything look good to people?
I thought it was different. The numbers were like,
Yeah.
It's like, I think there's like 44 plus something else.
Yes.
Yeah, okay. You know what must have happened? I must have copied this into this folder on my drive, but then I changed it on my computer before I printed it out. I think that's what's happening. I think it might have been a -8 or a.
I think it was 4 times 11.
Okay, yeah.
And because I remember it being 44 plus. Oh yeah. It's like that.
44 plus 32. Yeah, that looks better. So I must have changed the exam before I printed it out.
76 looks better.
Yes.
Okay, I was getting so stressed.
Okay.
I was like, I don't remember.
I forgot to recopy it to this folder. I don't know why I changed the numbers offhand. Maybe I was just trying to mix it up a little bit. Anyway, I might ask you on your final exam to show this work. On this exam, again, if you did this, I counted it as right, even if you didn't show this. And there was like 1 or 2 people at most that showed this work like that. But you should all be able to do that. A common mistake was that people put integrals here, and then they multiplied the final answer by 5, because the length of the interval is 5. But once you've actually used the given information, you don't need an integral sign anymore, and it'll give you the wrong answer. once we use the intervals that we're given. All right, back to the screen here. This next problem is L'Hopital's rule. And ideally, actually, if we'd had more time for L'Hopital's rule, I'd just have asked you to evaluate that limit and I wouldn't even tell you to use L'Hopital's rule. That would be more ideal, but we didn't spend a ton of time with L'Hopital's rule, so I gave you extra help. If you didn't know to use L'Hopital's rule, how do you know? How do you tell? And maybe for the final exam, if I put this on there, I won't tell you. Okay? It's because this is a 0 over 0 indeterminate form. Why? Because when you plug in x equals 0, what x is going toward, in the top and the bottom individually, you get 0 in both spots. Natural log of 1 of 0. 2 times 0 is 0. You can't just find this limit by plugging in 0. You'd be dividing by 0. You also can't find it by factoring and canceling the x. Because how do you factor natural log of 1 plus x? You can't. At least if you don't know a way to do that, at least. In Calc 2, there's actually a way to do that using what are called infinite series. So you have to use L'Hopital's rule. There's nothing else you can do here. And what you're hoping with L'Hopital's rule is you're hoping that you can get away with doing just g prime of 0 divided by h prime of 0 in this case. 0 because that matches this. X doesn't have to be going to 0 either, by the way. But the numerator and denominator have to be going to 0. Or infinity in the other form of L'Hopital's rule that I'm not going to test for now. As long as you're not dividing by 0 then, that'll work. And you won't be divided by 0. H prime of x is 2. The constant 2, so if you plug in 0, you get 2. Final answer here is 1. So that's what you do. Again, I'm not going to finish all these problems. I'm just going to remind you how to think about them. And again, for the final exam, I might modify it, and I might not tell you to use L'Hopital's rule. Again, zoom in if it's too small here. This problem, we have a function, cubic. Oh, I changed this as well. Okay, here's one way I changed it where I made it easier for you. You might remember on your exam that I actually factored the derivative for you. I found the derivative and I factored it for you. One thing that would make it a little harder is if I didn't do that. So this first version of the exam, evidently, before I read it, was harder than what you actually got. Maybe I won't tell you the derivative for your final, and maybe I won't factor it for you. Maybe it'll be more like what you see here. Here is the derivative. And yeah, I factored this for you on your exam. To give you critical points at -2 and 3. And what I told you to do in the directions now is to first verify which is a local max and which is a local min by using the first derivative test. And what does that say? It says to look at the signs, positive or negative, of the derivative in each of these intervals. Like you can plug in -3 over here, you can plug in 0 in here, and you can plug in 4 over here. It'll turn out this one is positive, this one's negative, this one's positive. That means f itself is increasing over here, decreasing in here, and increasing here. There's got to be a local max at -2 and a local min at 3. And you can use your calculator's graph to double check it. But that's how to show your work with this kind of picture. Not actually requiring you to explain in words. A picture like this is good. The second derivative is 12x minus 6. You check the sign of the second derivative at the critical points. F double prime of -2 is negative, the graph is concave down near -2, it's got to be a local max. F double prime of positive 3 is positive, the graph is concave up near 3, it's got to be a local max. Second derivative being negative means the graph is concave down. Second derivative being positive means the graph is concave up. Actually, I'm using a little bit more than just the sign. I'm using the fact that the second derivative is a nice function here, nice and continuous, and these things will be true. That would be the kind of working I'm looking for in part C. And then part D, you just plug in those numbers into the original function. The local max value is going to be at -2. The local min value is going to be at 3. Plug those into the function, see what you get. I think the local max might have been 49, and the local min might have been -70 something. If I recall correctly. Back to the screen here. This one seems difficult because of the extra parameters in there and the extra symbolism, but it's really the idea that I'm after, and it's the idea that's I've talked about a lot, actually, functions with parameters. You don't want to let the notation bother you, like the x sub crit and the y sub min. You don't want to let that bother you. You want to understand the idea. And if you're looking for some hints, some guidance in a problem like this, go ahead and use your calculator and make a graph, picking particular values for A and B, for example. Maybe A is 1 and B is 1, and see what the graph looks like. When x is positive, you'll see that it looks about like that. Kind of like a parabola, but not. It's got a vertical asymptote actually at 0, and it gets sort of straighter as you move to the right. Because this part of the function goes toward 0 as x gets bigger. In the long run, the function behaves like a times x. It's got a slant asymptote, actually. I didn't draw it perfectly. What's the critical point? It's a value of x. That's why I label it with an x. X sub crit. Just to emphasize it's a critical point. That's all. That's all the crit means. And the output there is going to be a minimum value. That's why I call it y sub min. But then I use function notation to say, hey, these depend on the parameters A and B. I didn't mark you off any points if you just wrote x and y here. I'm writing the extra stuff, the x crit of AB and the y min of AB, just for extra emphasis of what they mean. And that they do depend on A and B. Your answers depend on A and B. And I tell you the answers. So it's just a matter of actually doing the calculation. Find the derivative. You'll get A minus B over x squared if you do. Look at that formula right there. Let's quiet down, please. You get A. Differentiate B over x, that's the same as B times x to the -1. You'll get a -1 in front. B x to the -2. Which is what this is. Set that equal to 0 and solve for x. B over x squared will be A. That means if you flip both sides, x squared over B will be 1 over A. So x squared will be B over A. Take the square root of that. Positive square root because we are letting x be positive. And then part B, to find y min, all you do is you plug that into the function. Plug this thing into the function to find the minimum value. So what I was wanting there is for you to plug in the symbolic expression. It's easier to plug it in with the exponents, b to the 1/2, a to the -1/2, and simplify, and see that you get this. And if you do it right, you should get that. Plug it into the original function in place of x. So here's the initial calculation. There's a times x plus b times x to the -1. So this would be the proper kind of work to show right there for the -1 power. And then simplify. Use properties of exponents. That a has a first power, you got to add the exponents for the a. 1 plus -1/2 is +1/2. The b still is already to the 1/2. With this one, you've got to negate those exponents because you're raising the whole thing to the -1. You have to multiply that times each of those. So you get b times b to the -1/2 times a to the +1/2. And this also simplifies to a to the 1/2 times b to the 1/2. So in the end, you get 2 times a to the 1/2 times b to the 1/2, which is the same as 2 times the square root of a times b. F double prime of x just means take the derivative of this thing. A differentiates to 0 at the constant. This thing differentiates to back to positive 2b over x cubed. And we differentiate that part. And that's a positive quantity. B is positive, x is positive. The second derivative is always positive. The graph's got to always be concave up when x is positive. That is why you have the mean. It's a little bit more than what the second derivative tests say. It says the second derivative test only focuses on local means. But in fact, since the graph's always concave up when x is positive, it's got to be a global min. Though you didn't need to emphasize that point. There are a number of problems on, this page especially, maybe even on all these problems pretty much. A number of people just made them much more difficult than they were supposed to be. You made it too hard on yourself, okay? If you understand the basic concepts, the basic things I've emphasized, the problems are easier than you made them be. This is one example. You got a function that represents a velocity. That function can be both positive and negative. If you graph it with your calculator, you get something that looks about like that. And t is positive. That's the little f of t. That's the velocity. You start from rest, then you have a positive velocity for a time, so you're moving to the right. At this moment, your velocity is 0. That's when you turn around. That's the instant you turn around and start walking the other way. Your velocity is negative. And if you travel far enough for a long enough time in the other direction, your net change in position can actually be negative. The answer to this is actually 0 change in position. But how do you find it? The Fundamental Theorem of Calculus says that the change in position, delta position, or delta y or delta x, whatever you want to call it, is the integral of the derivative, the integral of the rate of change. Although using the notation you have here, that would be f of t is the actual rate of change, that's the velocity. The position itself is the capital F. So I'm using different notation, I'm not using prime notation. The other part of the FTC says to evaluate this, just do f of b minus f of a. And in fact, you don't even have to think of it in terms of integrals, even though I phrase it that way. You could just think in terms of f, capital F. F is it is an antiderivative, so it is the position. So to find the change in the position, do this difference over the interval from 1 to 3. So the final thing to do is to do capital F of 3 minus capital F of 1. Turns out to equal 2.25 minus 2.25. Final answer is actually 0 feet for the change in position. You start moving this way, turn around, and by the time, well, you start at time 1, by the time you reach time 3, you're back where you started. That's why the change in position is 0. But it's this difference. It didn't have to be 0, but it is in this case. This one's a related rates problem. Ladder sliding down a wall. try to point out common mistakes people made. Many people, when they drew this picture, labeled all the sides with numbers. That's a bad thing to do right away. Because things are changing. This distance right there is changing. The ladder's sliding away from the wall. This distance right here is changing. Call those variables. The length of the ladder itself is not changing. That's a number, 5 meters. But if you plug in numbers right away, you're missing the point. Okay? You're thinking about rates of change of things that are changing over time. And these things are related to each other. That's why it's called related rates. The Pythagorean theorem says x squared plus y squared equals 5 squared, or 25, for all time, for all t. Now you don't see any t's in the equation, but it's in your mind. Time is going by, the ladder is sliding. This is moving away from the wall, this is moving down the wall. You gotta have that perspective to realize what it's about. Both x and y depend on t. So when you differentiate now with respect to t, you have to use the chain rule in both spots. It's not like implicit differentiation where you differentiate y with respect to x and you use it in one spot. Both x and y depend on t. You get 2x dx dt plus 2y dy dt. The right-hand side is a true constant. It differentiates to 0. If it helps, go ahead and use function notation to emphasize x depends on time and g depends on time. Differentiate it this way instead, if that helps. And I did mention that. If you differentiate it this way, you get 2f of t f prime of t. Here it's a little more clear that you need the chain rule, perhaps, in both spots. That's why that might be worth doing. And to emphasize that x and y both depend on time. You solve for dy dt, you'll get this, and it's now at the end that you plug in your numbers. It's now you plug in the numbers. dx dt is 0.2. That's a velocity in the x direction. When the ladder is 3 meters away from the wall, y would be 3. Oh no, excuse me, x would be 3. You do have to figure out y using the Pythagorean theorem, using this fact. When x is 3, solve for y, you'll get 4. You should get a negative 3/4 times 0.2 here. The answer is, before you take the absolute value, the answer is negative 0.15 meters per second. But then you want a positive quantity because it's phrased as how fast is it sliding down. So you take the absolute value, the answer is 0.15 meters per second. But lots of people just don't even realize it's a related rate problem. And some people realize it's related rates, but then they make mistakes. You got to use the chain rule in both spots. This is of the form inside function f of t and an outside function, the squaring function. The chain rule says take the derivative of the outside, bring the 2 down, subtract 1 from the exponent, multiply times the derivative of the inside function. You might be more comfortable with this notation, but this notation is more standard. This is our typical minimize the surface area problem that we spend a lot of time with, except I'm plugging numbers in and saying the volume is 10 cubic centimeters. The surface area is 2 pi r squared plus 2 pi r h, but you want a function of one variable. You don't want the h to be in there, so you have to use the constraint. You got to replace h with 10 over pi r squared. And that was something that I made a little easier on your version of the exam. I actually told you what h was. Then simplify this before you differentiate. The pi's cancel. The 2 and 10 combined give you a 20. One of the r's cancels. There's your function that you want to minimize. So take its derivative, set it equal to 0, solve for r. The final answer for R turns out to be about, I believe, 1.17 centimeters, I think. Or something close to that, at least. And H turns out to be double that, like 2.34 centimeters. Turns out to be the answer, I think. So again, I'm seeing lack of understanding on many of this. Okay, I'm seeing people just sort of scribbling a bunch of stuff, not clear what to do. Okay, it's probably because you just didn't practice the old exam questions enough, or doing the old homework problems enough, and maybe you didn't go to math lab enough. Okay, or my office hours. I was trying to emphasize during the semester, you got to take these completion homework assignments seriously, and if you don't understand, you need to get help. You need to go to office hours or math lab. And I know some of you did, but maybe not everybody. That should have. $14, all you needed to do was understand what I meant when I said how to check a function's solution of the differential equation. The function's x squared. The differential equation is dy dx equals 2y over x. How do you verify this is a solution, or maybe figure out that it's not a solution? What I've been telling you is the exact way to do it. Take the left-hand side of the differential equation and evaluate it for this function that I'm wondering, is it a solution? So I got to differentiate. I've got to find out prime. I'm writing an f prime of x there. I could just write a dy dx. That's 2x. And the right-hand side is 2y over x. You got to remember, y is the function. You need to replace y with the function and see if it simplifies to the same thing. The function is x squared, and it does simplify to the same thing. We have a match. That means yes, it is a solution. That's all you have to do. Okay? If you don't have a match, then it's not a solution. So if I gave you some other function like x cubed and said is it a solution or not, you would see it's not actually, I believe. The left-hand side is the derivative. That's 3x squared. The right-hand side is once again 2y over x, 2 times the function over x. The function's x cubed. 2x cubed over x simplifies to 2x squared, not a match. Not a match. So this would not be a solution. They have to be equal for all x where they are defined. Now these are equal when x is 0, but that's not for all x where they are defined. These are equal for all x when they are defined. Technically speaking, this one's undefined at 0, so we don't worry about that. These things are equal wherever they're defined. $15 was your density function data modeling problem, except I didn't actually give you any data. To figure out, does this density function model data where the data is most dense for low values, medium-sized values, or large values? The point is to graph the function. Use your calculator and graph it, and you graph something about like this. Because the graph is higher over here, that means the data is more dense there. The height of the density function, that's why it's called a density function. The height determines the density. In fact, if you multiply the value of the density function at some point times a certain length of a certain interval, you'll get the percentage of the data in that interval. So when the graph is higher, you're going to get a higher percentage. When it's lower over here, you're going to get a lower percentage. But the point is the graph's high over here, it's going to be in low values where the data are most dense. As far as finding the percent of the data less than or equal to 5, you just plug it into the CDF. That's the point of the CDF. F of 5 is the answer for part B. And I did say that in the lectures. Okay? Capital F of x, the cumulative density function I said in the lectures is the percent of the data less than or equal to x. Or approximately, because these things are models, they're not perfect reflection of reality. So f of 5 is going to be the percent less than 5. And if I recall correctly, I think it turns out to be 0.75, I believe. 75% of the data are less than 5. Which makes sense because the data are denser in the lower values. So even though 5 is only halfway between 0 and 10, the data is so dense over here that 75% of the numbers over here and only 25% in here. But this is all you have to do. Okay? Just plug x equals 5 into the CDF, the capital F function. And there's a reason using these letters, lowercase and capital F. That's because capital F is an antiderivative of little. The derivative of capital F is little. You can check it if you want. If you differentiate this, you'll get 1/5. Imagine that 1/5. Bring the 2 down here, 2 25ths minus 2 25ths times x. We subtract 1 from the x, and we get x to the first power. The derivative of this is that. And graphically, you should also understand I might put this on the final. You should understand how to find this value graphically. If you graph capital F here, maybe I would actually graph it for you, just for the final example. The graph looks about like this. Something about like that is what capital F looks like. And when you plug in 5 into that, the output is 0.75. Just like I said. So 75% of the data are less than 5. And that's all you have to do. That's the way these models work. They're set up to work that way. It's nothing magical, it's just they are made to work in this way. I was surprised at the difficulty people had with this one. I was expecting most people to get this fully correct here. But the especially surprising part was part B. We should spend a lot of time on distance and speed. Now I know you may not have used parametric mode on your calculator like I suggested, but you could plot points like I suggested during the exam. For example, when t is 1, you're at the point 1, 1. Think of that as a point 1 coming. You can find it when t is 1.5. When t is 2, for example, you're at the point 2 forward. When t is 0, you're at the origin. These are points on the graph. And you move in that direction as t increases. You can plot more points to be more sure, but the graph looks about like this. And it's motion in that direction as t increases. Most of you got that part right. There's more trouble for part B. We want to verify the speed is the square root of 1 plus 4t squared. That's not meant to be difficult because it's just a formula. It's just this formula. And since f of t is t, and g of t is t squared, you take those derivatives, f prime is 1, g prime is 2t. Simplify a little bit, and you get the answer. And then in part B, or part C, excuse me, you're trying to find the distance traveled. That's the integral of the speed. This graph is the speed. Go back to the screen there. This graph is the speed. So I said you could use your calculator to approximate the area under the curve. And the calculator will be more accurate than the right-hand sum would be. But if you didn't know how to do that, I did draw the picture with the rectangles in there to be suggestive as to what you can do. A right-hand sum, RHS in this case means right-hand sum, would be the area of this rectangle. Take the right endpoint, plug it into the speed function, speed of 0.5 times the width of the rectangle, which is 0.5, plus speed of 1 times 0.5 for the second rectangle. For the third rectangle, it's speed of 1.5 times 0.5. And for the last one, it's speed of 4 times 0.5. And by the way, even if you use your calculator to get the answer for the area under the curve, you should still know how to do right-hand sums. Maybe in the final, I will just ask for a right-hand sum. This is what you would do. That red graph is the speed function. We're trying to find the area under it by adding up the areas of these 4 rectangles. Each of these terms is a height times a base. The base is 0.5 in each case. I don't remember the answer offhand. I think the more exact answer is 4 something meters, and the approximation you get with the right-hand sum turns out to be 5 something.
For the speed, why didn't you take the square root of that?
There's a square root there.
Yeah, but like how? Why?
The formula involves a square root. The reason I gave was because the speed is the length of the velocity vector. And from the Pythagorean theorem, that means its length will be the square of the side, the square root of the square of the length of that side plus the square of the length of this side. And I did say this is the velocity in the x direction, which is f prime of t, and this is the velocity of the y direction, which is g prime of t. So that's how to understand the formula. But as far as doing the problem, you just use the formula. I said I wasn't going to actually test your vectors. Right? You can find this formula in section 4.8. With dx dt and dy dt notation on page 252. You can also write this. Come over here further with camera. As square root of dx dt quantity squared plus dy dt quantity squared. That's the way the book writes it. But it's the same thing. Take the derivative of f and g and square root of f. If you understand integrals giving you signed areas, this problem is not too hard either. But you got to understand it. You got to realize the integral gives you the change in volume in this case. I did make what you might consider to be a minor typo when I wrote this, and I didn't fix it in the final version. It probably would have been good if I had put the word net there as well. I just forgot to. Technically speaking, when you talk about a change in a function, it can be positive or negative. You don't really need the extra word net in front of it. It's there just for emphasis, to say that it can be positive or negative. If you interpret that without the word net in there as a total change, both water going in and water going out, and you added the areas, I gave you full credit, even though I was really after a difference. I realized I probably should have put the word net in there since the word net was elsewhere. On your version of the exam, I did have the word net there, but I forgot to put it there. The change in volume is the integral of its rate of change. In this case, from 0 to 4. R is the rate of change. Now I'm putting a t there. In the problem statement on the screen here, I put a u there. It doesn't matter. I have a variable upper limit of the integral here. As time goes by, you would imagine the shaded area moving to the right here and then going down here as t goes between 2 and 4. The signed area function would increase at first. Then once you get into this region, the signed area function would decrease. The signed area being the integral, being the change in volume. And by the signed area interpretation, the answer is 9 minus 5, 4 gallons. We should subtract. That's the change in volume. If I put this problem on the final exam, I'll put the word net in there in both spots. Or I really don't need it. You know, if I had drawn this area were bigger than that one, say this is 9 and this is 15, of course the drawing would look different, then the change would be 9 minus 15, negative 6. The total change in volume would be downward in that case. The areas don't have to, well, the flow rate doesn't have to start out positive and then go negative. It could start negative and then go positive. The outflow could be faster than the inflow at first. If I had a graph that looked like that, you take the area over here minus the area over here. The principle still holds. As far as the volume itself at time 4, the volume at time 4 would be the initial volume plus the change of volume. Just do 2 plus 4 to get 6. That's all you have to do. So you can see it's not a complicated calculation in this kind of thing. It's understanding concepts. You gotta have a conceptual understanding of what these symbols and ideas mean. It's higher than the starting volume because more water flows in than flows out. This area is bigger than that area. It could have been lower if this one was bigger than that. But I do mean an actual volume here, so I'm not going to give you a problem where the final volume ends up negative. Some of you got a negative answer, and a few of you who got a negative answer said, this doesn't make sense, but this is what I got. You can have a negative position, you can't have a negative volume. At least not in our universe. Maybe some other universe you can. With the proof, vast bulk of our time is in exam 3, but I think this is definitely worth it because this was the hardest one for people. Besides the fact that you didn't have as much time as I wanted. You want to use the constant function theorem here, right? Because you want to show that this function is a constant for all x. So that should ring bells off in your mind saying, hey, to show a function is constant, I need to take its derivative and show it's 0, always, for all x. That should be going off in your mind as you start reading the problem. And I started for you. I said, okay, by the chain rule, h prime of x is, I want you to finish that. H of x is f of x quantity squared minus g of x quantity squared. So by the chain rule, its derivative, this is pretty similar to the related rates problem, except it's a derivative with respect to x instead of t. 2f of x, f prime of x, minus 2g of x, g prime of x. Right, because I bring down the 2 in both cases, subtract 1 from the exponent, and then multiply times the derivative of the inside function. That's the chain rule. And then use your assumptions. You also should have light bulbs going off in your head saying, I have to use my assumptions in some way. Otherwise, why am I doing this? These assumptions are relevant. F prime always equals g, and g prime always equals f. So make those substitutions. Replace f prime of x with g of x. Replace g prime of x with f of x. And then you look at that and you say, hey, those are the same numbers I'm subtracting. This is always 0 for all x. So by the constant function theorem, that means h of x must be constant for all x. But wait a minute, the final thing to do says to show that constant must be 1. That's how those pieces of information are relevant. This is constant for all x, but when you plug in x equals 0, by the formula for h, you get this. And using the fact that f of 0 is 1 and g of 0 is 0, you get 1. if h of x is a constant for all x, and its value at one particular value of x is 1, then h of x must always equal 1. For all x. And it's really good to put the for all x's in there all the time, because it really emphasizes what it all means. That's what you're really trying to do. That's the point. Is to show h of x equals 1 for all x. Its graph is horizontal. Okay? Question? I'm saying I'm taking from old exam problems, so this proof could be on it, maybe modified. One way it was modified, I think in class or in your homework, one of those two, is the assumption was f prime equaled g, but g prime equaled negative f. And we try to show that f of x squared plus g of x squared was a constant. An example of a slight kind of modification. All right, we're low on time. So what can we do in 8 minutes? Just briefly, quickly go over exams 1 and 2. So exam 1, we went through the beginning of chapter 2. So that was a review of pre-calculus, as well as a little bit of calculus related to limits and basic derivatives. So a lot of these things are pre-calculus kinds of questions, just knowledge about asymptotes, about dominance. For example, here, this one's kind of extreme. I did that on purpose. Even though this function grows really fast, much faster at first than this one does, in the long run, this dominates because it's exponential, whereas this one's a power function. Exponential functions, even when the base is just barely bigger than 1, will dominate any power function, no matter how big this number is and no matter how big that number is. It's just a fact to know. Knowing the definition of logarithms was on that exam. Using a trig identity here, this one, and thinking about the quadrant the angle is in. Theta is between pi, that's between 90 degrees and 180, you're over in the second quadrant. The cosine is the first coordinate, so that would be negative over there. The sine is the second coordinate, so that would be positive. Thinking about the unit circle bug definition that I called it, about cosine and sine. Solving for an inverse function is another example. You don't have to swap the variables. It's up to you. Just get the right formula. Use an inverse trig function to solve an equation, a trig equation. And if I put this on your exam, I'll probably put an extra credit for it again. Find a polynomial function that has this graph. It's just a matter of realizing what it would look like in factored form because the roots are being in -1, 1, and 3. And then getting the right y-intercept, so you have to allow a coefficient in front that helps determine the y-intercept is 6. On this one, we're talking about height of an object as a function of t, going up or down, and the influence of gravity. There's your typical kind of formula way over there on the right. An average rate of change is that kind of computation, and graphically it would represent a slope of a secant line. Its units would be feet per second, looks like here. I didn't ask for an instantaneous velocity. I could, on your exam, take the derivative and plug in whatever instant time you happen to be talking about. This is a problem-solving kind of thing related to linear functions. This next one is about proportionality. Proportionality to r to the 4th. You got to figure out k and then use it to solve the problem. I think most of you did pretty well on that one. Find a sinusoidal function that has this graph. This was a harder one. Okay, you got to figure out the amplitude and the period and the vertical shift and the horizontal shift as well. Use a cosine, and it's probably the best choice because the high point would get shifted from the origin to over here. For a cosine graph, that would be a rightward shift by 3 units. That's probably the best one to use. It's a limit calculation involving doing a trick first to help you figure it out. We talked a lot about holes in graphs back here and vertical and horizontal asymptotes for rational functions. You do want to cancel the x minus 3's here before you simplify. And because of that cancellation, the graph will actually just have a hole at x equals 3. Whereas x equals -4, there would be a vertical asymptote. If that x plus 4 does not cancel. And use that to evaluate a limit. Limit definition of the derivative. I think I probably can't avoid putting a limit definition of the derivative problem on your exam. It's just too important. That probably will be a type of problem that shows up on the final exam. Make sure you practice it. And if you're unsure if you're doing it right, work together at it. This is a proof, so I suppose this could show up on the final exam involving the properties of logs. So you want to look back at your notes. We did that kind of proof in class. This is an exponential growth problem. You have to do some solving using the logarithms there. On exam 2, that was mostly chapters 2 and 3. Definition of the derivative, basic applications, second derivative, local linearity, tangent line approximations, units. Then chapter 3 got into the standard rules, linearity, product rule, quotient rule, chain rule, gateway kind of facts. And what else? Derivatives of inverse functions, logarithms, inverse trig. And at the very end, there was the theorems, including the mean value theorem. So just true-false questions related to factual information. Here's a derivative problem. Kind of a complicated derivative like you had in those quizzes. So you should practice. It's worth practicing that. I might put that on the final, that type of problem. Here's a derivative fact related to inverse functions. People had trouble with this one. The most important thing to realize to help you finish the problem is that since f of 2 is 13, that means f inverse of 13 equals 2. They switch around. So that's something important to help you finish this problem. You did pretty well in number 8 using different rules. Slope of a tangent line based on using implicit differentiation here. So here's where you differentiate everything with respect to x. Differentiating x cubed with respect to x does just give you 3x squared. Differentiating y cubed with respect to x does not give you 0, and it does not give you 3y squared. The chain rule must be used. You would get 3y squared dy dx. Because you're assuming y depends on x, that's why. It's not a constant. People have trouble giving reasons for their steps on a derivative problem like this. You should look back at that old exam I did typically say what the reasons are. If you got it wrong, and most people did not get full credit on this. Exponential problem again on this exam, including how fast is the population changing, so that's a derivative. This one is about Newton's law of cooling in a sense, although you don't actually have to work with the differential equation. You just need to interpret the meaning of these things, what it looks like, to draw a graph. Free fall problem, solve for different things. And this is the last page. This one was to approximate something in a couple ways. This first part was to use local linearization, and the second part was to use Newton's method. And looks like this was not the final version of your exam either. There's evidently a last problem here that I did not have on here yet. You could look that up on your exam too. Okay? So we spent a lot of time today on integrals. Definite integrals, thinking about the fundamental theorem of calculus, focusing on exam 3. That was the thing that people had the hardest time with. But if you focus on those key principles, they're not as hard as it might have seemed at first. Just be calm and realize, okay, if I understand basic principles, I can do these things. Thank you for being in the class. We'll see you next week.